Hello, I'm Cornelia. I'm an applications engineer working on the products Avizo and Amira, and I will be the host of today's tutorial on meshing. This tutorial is the last of a series of 3 lessons. In the first 2 lessons, we discussed the basics of using the meshing room and then entered into the details of the advanced use of meshing refinement options. If you haven't watched the videos yet, please do not hesitate to do so before following this tutorial. In this last lesson, you will learn how to perform the optimization of mesh quality and the color mapping of material properties. The tetrahedron node location can be optimized in order to reduce the amount of sliver in the mesh. A sliver tetrahedron is formed by placing its 4 vertices near the equator of its circumsphere, or specifically having a flat tetrahedron. Slivers may slow down the convergence of numerical simulation, meaning that the less sliver in a mesh, the better. The optimized mesh option aims at reducing the amount of sliver by perturbing them through random vertex relocation. The mesh generation may be slightly longer if this option is activated. The option is available whether the fast meshing option is on or not. Keep the previous settings and in the global parameters section, select the Optimize Mesh checkbox. Select kernel-corn.labels.tetra in the mesh field and click Replace. Now, kernel-corn.labels.tetra and kernel-corn.labels2.tetra are the optimized and non-optimized versions of a mesh generated with the same parameters. You can now compare their quality in terms of number of slivers. In order to do so, first go to the project workroom, attach a Tetra Grid View module to each mesh, and for both, click Show or Hide, then remove in the buffer port to select all Tetra and then hide them all in the viewer. Select kernel-corn.labels2.tetra, the non-optimized mesh, and click the Grid Editor button in the Properties area. In the selector port, Tetra quality is selected. Press Select. This selects tetrahedra according to the quality measure defined in the next port. Capital R inferior to 0.02, where capital R is the ratio of the radii of the inscribed and circumscribed spheres. Capital R reaches its optimal maximal value of 1/3 for an equilateral tetrahedron. Slivers are detected by a small value of capital R. The viewer now displays the slivers of the non-optimized mesh. You can also retrieve their number from the console by clicking the application's lower right corner button. Toggle off the visibility of the Tetra Grid view attached to kernel-corn.labels2.tetra. Repeat the previous actions on the grid editor of the optimized mesh kernel-corn.labels.tetra. You can see in the viewer that there are less slivers in the optimized mesh. The console displays the number. You can observe that there are much less selected tetrahedra. It is possible to further improve the quality of the mesh using the grid editor. In the modifier port, select Repair Bad Tetras. Press Modify. Press Select again in the selector port. In the console, you will notice that the number of slivers has further decreased. For the purpose of the next section, remove both TetraGrid View modules. The previous sections illustrated in depth how to refine the mesh and how to optimize it. This following section is dedicated to color mapping of material properties. Scalar fields can be color mapped on the mesh to visualize material properties. For instance, you will now visualize curvature information. In the project workroom, attach an image curvature module to the label field. In the interpretation port, select 3D and press Apply. Attach a Tetra Grid View module to kernel-corn.labels.tetra. Set the maximal local curvature kernel-corn.labels.curvature as color field of the Tetra Grid View. Set the color map to physics.icol and the range to -0.8 to 1. To discretize the scalar field per cell and per node of a tetra mesh, you can use the arithmetic module connected to both the mesh and the scalar field. Attach an arithmetic module to the kernel corn.labels.tetra. Connect the input B of the arithmetic module to the curvature field. Set the expression to B. Result location field can be set on nodes or on cell center. Try both. Attach the tetra grid view color field to the results of the arithmetic modules in order to map the curvature field to the mesh. To summarize, in this lesson and in the previous ones, you should have seen how to generate and inspect the mesh, perform a global mesh refinement, individually refine groups of materials, set the boundary conditions and export to finite elements analysis solvers, and perform an advanced mesh refinement, a boundary layer refinement, the optimization of mesh quality, and the color mapping of material properties. Thank you for watching this tutorial on advanced meshing. We hope you found it useful and that you will join us again for other video tutorials on Avizo and Amira. Goodbye.